Today we're talking about applications of exponential functions, which is something that we did last year. So this should be a review. So we talked about different compounding periods, which is a equals p times 1 plus r over n to the nt power, where a is the amount of money in the account at any time t. The r value is the annual interest rate, p is the principal or starting amount, n is the number of compounding periods, each year, and t is the number of years. So suppose you invest $1 for a year at 100% interest rate compounded n times per year. So we're going to do the different compounding periods with annually, which is once per year, semi-annually, twice, quarterly, 4, monthly, 12, etc. So as you can see, if we invest this dollar at 100% during these different compounding periods, the more and more you are reaching this value right here, which is the number e. So that takes us into continuously compounding in the number e. The more you compound, the more the final amount will be. There is a limit that is reached, which of course is e. And if we remember from last year that e on our calculator, you can get to by hitting second and the division symbol, or you can do second and the ln button, which takes it to a power. So two different ways of getting your e value. Continuously compounded are the keywords for using a equals pe to the rt formula. So when your compounding periods increase without bound, so a is the amount after t years, dollars invested is your p, r is the annual interest rate compounded continuously, and t is the time in years. Of course, e is just a number, so you're not plugging anything in for e. It's not a variable that you're plugging something in. So for the first example, it says determine the amount that a $5,000 investment over 10 years at an annual interest rate of 4.8% is worth for each compounding period. So go ahead and pause the video and do this on your own. When you're done, you can unpause and check your work. So for the first one, if we're talking about compounding annually, we know we're using a is equal to p times 1 plus r over n to the nt power. So we have to figure out each of the different variables. So p is our starting amount, which was $5,000. And our r value, which is the rate, was 4.8%. So as a decimal, 0.048. N is the number of times we're compounding. So in this case, n is equal to 1 since it's annually. And our time, it told us in the problem, was over 10 years. So t is equal to 10. So when I plug this in, I get a is equal to 5,000 times 1 plus 0.048 over 1, because that's our n value, and then 1 times 10. So that would be our equation, and then we would plug it into our calculator to get our solution. And I would practice plugging these into your calculator because often students get the final answer wrong just because they didn't plug it correctly into the calculator. I see it quite often, so I would always check to make sure. And so when we plug this in, our first answer is $7,990.66. Since we're talking about dollars, we're going to round to the nearest hundredth. All right, so looking at the next one. All right, for the next one, we're compounding quarterly. So we're using the same formula, a equals p times 1 plus r over n to the nt power. So again, my p is the same, still 5,000. R is still 0.048. N now is quarterly, which is 4, and time is still 10 years. So a is equal to 5,000 times 1 plus 0.048 over 4 to the 4 times 10. And then you're going to want to plug this into your calculator. So I'm just going to do this, use the other equation. So we have now divided by 4 and 10 times 4 power. If you have an older calculator, make sure you use parentheses for your exponent, otherwise it might think you're multiplying the whole thing by 4. So here we get $8,057.32 when we round. which makes sense because the more you compound something, the more money you should get. And the next one's compounded monthly. So again, same formula. So P is still 5,000. R is equal to 0.048. N is now equal to 12 for monthly, and T is still 10 years. So A is equal to 5,000 times 1 plus 0.048 divided by 12 to the 12 times 10 power. We're going to plug that into our calculator. Oops. And if I hit enter, I get $8,072.64. And the last one, we are compounding daily. So now our end value is going to be 365, and all the rest of the values are the same. So if we plug this into our formula, A is equal to 5,000 times 1.048 divided by 365, and 365 times 10. And again, plugging in your calculator is half the battle. So this is now times 365, and same down here. And so we get $8,080.12. What if instead we had one of these as compounded continuously? So I added another one here, E, which says compounded continuously. So anytime you see compounded continuously, those are the keywords to know you're using A equals PE to the RT formula. And in this case, we're trying to find the amount. 5,000 is still our starting amount, times E, and our rate was 0.048 times time, which is 10. So if we're compounding continuously and we plug this in, we would get 5,000 and then E to the 0.048 times 10, which gives us $88,080.37. Which makes sense that it's a little bit more than when we compounded daily, because again, the more and more you compound something, the more you should have in your account in this case. So let's go ahead and look at example 2. So it says if $7,000 is invested at 5% annual interest compounded monthly, when will the investment be worth $8,500? So go ahead and pause the video and see if you can do this one on your own. When you're done, unpause and we'll take a look at it. So compounded monthly tells me I'm using A equals P times 1 plus R over N to the NT power. And in this case, our P is $7,000. Our R value is 5%, so 0.05. N is compounded monthly, so 12. And in this case, it's asking when will the amount be worth 8,500. So now we have the A, which is 8,500, and we're solving for T. So if I plug this in, we have 8,500 equals P, which is 7,000, times 1 plus 0.05 divided by 12 to the 12 times T. So we solved these last year in our logarithmic unit. So if you recall to solve, you first, you're doing the order of operations backwards, PEMDAS. So you would first get rid of things that are added or subtracted. which we don't have on the outside, then you would get rid of things multiplied or divided, then parentheses, or exponent, excuse me, and then parentheses. So we can't get rid of the things that are added inside the parentheses. So we don't have anything added or subtracted on the outside, but we do have that 7,000 being multiplied, so we want to divide that out. So for this, we're going to go ahead and leave it in fraction form. So if you reduce, you get 17 over 14 is equal to 1 plus 0.05 divided by 12 to the 12t power. Now we do the exponent. So remember, when you're solving for a variable exponent, you have to use logarithms in order to bring that down from the exponent. So that would be logarithmic form. So remember, the base stays the base. So what's the base here? It's 1 plus 0.05 divided by 12. So 1 plus 0.05 divided by 12. And then of 17 over 14 is equal to your exponent, 12t. And then the last step would be to solve for t by dividing both sides by 12. So to plug this into our calculators, remember we learned about the log button in our calculator. So if you go to math and scroll all the way down, you have that log base button. So if we plug that equation in, so we have in our base 1 plus 0.05 divided by 12 of 17 divided by 14, and enter. And you end up with, missing here, and of course we have to divide by that 12 and divide that by 12, and we get t is equal to 3.9 years. Almost forgot to divide that 12 out. So now we have our answer. You could, of course, plug this into your y equals and look at the intersection. So you could plug it into y1 and y2. So if I plug it into y1 and y2, the hardest part is actually finding the window that's correct. Notice that in y1 I have 8,500, so that means that my window needs to be a lot larger than what I'm looking at here for my y values. So 8,500 would have to be above that. Oops. So let's do 8,600. And we know it's not going to be negative. And these increase very fast. So I'm just going to do 10 there. And you could put 0 here if you want. So here would be our graph. So you can see it's going to hit somewhere in there. Right around 3.9 years, we already know. Second trace. Number 5 is intersection. And you hit enter 3 times to guess, and again you get the same answer. However, it is important to know how to do the logarithmic way of being able to find this, because we will be solving logarithmic equations later, but that's just, again, another way to solve the problem. Looking at example 4, it says if you invest $3,500 at 3% compounded continuously, so that's your keywords right there to tell you you're using A equals PE to the RT power. How much is in the account at the end of 4 years? Go ahead and pause the video and see if you can do this on your own, and on pause to check your work. So A is equal to P, your starting amount is 3,500 times, of course, E is just the variable E, the number E, I should say, not the variable. So in your calculator, you would use that. And then we have the rate, 3%, so 0.03 times time, which is 4 years. So if I plug that into my calculator, I get 3,500 e to the 0.03 times 4. So $3,946.24. All right, for the next one, it says When tap water is filtered through a layer of charcoal and other purifying agents, 30% of the chemical impurities of the water are removed. If the water is filtered through a second purifying layer, 30% of the remaining impurities are removed. How many layers are needed to ensure that 95% of the impurities are removed? So for this problem, if you look at it, do you see any of the words that say compounded monthly, annually? No. And we also don't see compounded continuously or any words like that. So then what kind of a problem is this? Well, if you recall, we're talking about solving exponential equations. So this is just an exponential equation, which is y equals a times b to the power of x. So for our exponential equations, remember that a is always your starting amount, and b is always the growth or decay factor. We talked about that in Math 3 and also Math 1. And so remember that the equation for b is 1 plus your rate. So if we want to solve this, then think about what we're trying to get. We're trying to ensure that 95% of the impurities are removed. So what's our starting amount then? Well, we start with 100% of something, right? So 100% or 1. And our rate, in this case, says that 30% of the chemical impurities are removed. So minus 30% or minus 0.3. So then in this case, x is going to be the number of layers removed. Or number of layers to remove the 95% impurities. And if we look at our r, notice that's not in the actual equation, so that means we need to solve for our b value using our r. So b is equal to 1 plus our rate, which is minus 0.3. So your b value is actually 0.7. And we are solving for x, so that means we know what y is. So remember that you want 95% of the impurities are removed. So remember, if you're talking about 100% of something, then what is left from that 100% if 95% is gone? Well, 100 minus the 95 gives us 5%. So your y is going to be 0.05. So if we solve this equation, we have 0.05 equals 1 times 0.7 to the power of x. And this is what we're solving. So if you divide by 1, that doesn't do anything. So in order to solve this equation, we're solving for a variable exponent. We again use logarithms to help us solve. So the log, the base stays the base of 0.7 of 0.05 is equal to x. If it helps, recall if you have the base with the exponent equals the answer. In logarithmic form, it's the log of the base of a equals e, if that helps you to go from one form to the other. So now when I solve for x, I end up with x being equal to 8.4 layers. But of course, we can't have a part of a layer, and we want to ensure that 95% of the impurities are removed. So that means that 9 layers are needed to ensure that 95% of impurities are removed. All right, so example 6 is similar to the one we just did. So you do this on your own. Looking at the next one, we're talking about half-life. It says radioactive decay because I think that's for the problem, but we're just looking at half-life. So if you recall from last year, this is our half-life formula, where A is the final amount, P is the initial amount of the substance, X equals 0 corresponds to the time when the whatever it is that you're talking about, it doesn't have to be radioactive decay, it could be whatever it is when the decay began, and H is the half-life. So for the first one, it says, after a living organism dies, its carbon-14 decays exponentially. An archaeologist determines that the skeleton of the mastodon has lost 64% of its carbon-14. The half-life for C14 is 5,730 years. Estimate how long ago the mastodon died. So for this, notice again, we're not talking about compounding continuously or annually or anything like that. So that's how we know we're not using those formulas. And the key word is, of course, half-life, tells you using the half-life formula. So in this case, your starting amount, just like the chlorine problem, you start off with 100% of the living organism, which is the mastodon. So 100% which means that P is 1. X in this case, because it's the half-life in years, so X is going to be the time in years. Since our half-life is 5,730 years, so H is equal to 5,730 years. And our amount, it says it has lost 64% of its carbon-14. So if you started with 100% and you've lost 64%, 100 minus 64 gives you 36%, or 0.36 is left. So 0.36 equals 1 times 1/2, or 0.5, X divided by 5,730. So the next thing we do is solve. We can use our logarithmic form. So the log of the base, which is 1/2 of 0.36, equals X over 5,730. And then the last step would be to solve for X by multiplying both sides by 5,730. And so when we plug this into our calculator, we get math log base. You can either write 1/2 or 0.5, doesn't matter if you use a decimal. So 0.36 times 5,730. So that means it died, the mastodon died 8,445.6 years ago. And that's it. So hopefully taking a look at each of these problems is reminding you of, Math 3 when we did these problems last year. So make sure you know those formulas, and of course how to solve when you're solving for time using your logarithmic equation if needed. And that's all for today.